Hello everyone, and welcome to a very nice and relaxed video of functions of two variables. Actually, in this video, everything is going to be very cool in the sense that we're not going to do a single computation. The purpose of this video is just to give you some visual representations of things or some of the things that we've done so far. For example, or in particular, we're going to look at what is the graph of a function of two variables. We're going to talk also about what does it mean to compute the partial derivative f of x and f of y, at a point a, b. We're also going to talk about, because this is something that we do a lot for functions of one variable, when is my function reaching a maximum or a minimum? What does it look like for functions of two variables? Is there any other type of special points like this, maximum, local minimum, or critical points? And the answer will be yes. There's also saddle points for functions of two variables. So we're really just going to give you some visual information. But of course, the ultimate goal, and this is not something that we're going to do in this video, will be to then compute these things, because it's going to be very important. If you have a function of two variables and you want to, suppose that function of two variables is modeling the profit of your company because you're selling 2 units and you want to maximize profit, or if you have a function that is modeling cost, then you want to minimize cost. But now you have equations, so how do you find these things algebraically? And this is what we'll do in the next video. But for this one, things are cool. Okay, so let's start first with the graph of a function of two variables. So to help us here, I'm going to use a goat, okay? Because I find when I use a goat, sometimes it helps to really understand what's going on with these functions of two variables. So here, the first definition is, what is a graph of a function of two variables? So here, remember, for functions of two variables, there's 2 inputs. So you're starting somewhere on the Cartesian plane. When you are visually representing the domain of a function of two variable, you're talking about a region in the Cartesian plane. So suppose we start at a point AB in the domain that we have here in blue. When you compute the output of the function, then the value that you get will be a point with a z coordinate. It's going to be strictly positive if it's above the ground. It's going to be 0 if you're on the ground, and it's going to be negative if you're below the ground. And then if you look at the set of all points where AB is in the domain, and then where the z coordinate is the value of the function, so AB is in the domain and the z coordinate is f of AB, then if you look at the set of all these points, you're going to look at a surface that floats, like a blanket that floats in space. And here, just to show you what's going on, so suppose you start at AB and you compute the output, you're at AB, f of AB. So my goal here is on the graph, on the surface, on the land of this graph. And then if you look at the set of all points on the graph, if you look at the surface, so the goat can kind of walk on the graph here. So this land here, so you can see the goat can go up to the top of a mountain. We're going to call that the local maximum in a moment. You can actually go in the middle there. There's the bottom of a lake. There's also those weird points that we're going to call saddle points. So anywhere this goat can walk is the graph of the function f of xy. And this is really like the 3D analog of the graph of a function of one variable. So if you remember in calculus 1, for functions of one variable, if you have a point A inside the domain, so if you start with a point A inside the domain and you compute the output of that point, you get a value for z. So the set of all point of the form A f of A will give you a curve in R2. And now if you're thinking about the goat here, so if it starts at AF of A, so where it can walk is the graph of a function of one variable, but it's a curve in the plane. Meanwhile, the graph of a function of two variables is a surface in R3. And sadly, as soon as you study functions of more, strictly more than two variables, or 3 or more, you can no longer visually represent the graph of a function of of three or more variable, because you cannot say, like, for example, for functions of three variable, it's some sort of 3D object in a four-dimensional world. It's really, really creepy and very, very extremely difficult to visualize. But anyways, so just to recap, the set of all point AB in the domain, f of A in f of AB being the z coordinate is going to give you a surface. So the graph of a function of two variables. Sorry, the graph of a function of two variables is just a surface in space. Okay, so in R3, just like the graph of a function of one variable is just a curve in R2. All right, got a bit confused there at the end. Ben là, ça doit être le vin blanc là. All right, let's move to the next important thing. The next one is we've computed partial derivatives, f of x and f of y. What do they mean, like on the graph of a function of two variables? So here, if you think about your function, suppose you have a point AB. So you start with a point AB in the domain, and then you evaluate your function at AB. You're going to be on your graph. So here we go. Let's bring the goat at that point. So the goat is at that point. So when you compute f of x and f of y, and you evaluate these two functions at the point AB, you're going to get two numbers. Because remember, f of x or f of y are just two other functions of two variables. So when you compute these functions at a specific point, if you evaluate this function at a specific point, you're going to get two numbers. Now, if you are computing, for example, f of x at AB, the number that you get actually is represented here by the slope, as if the goat is going to travel in the same direction as the x-axis. So if the goat moves parallel to the x-axis, then it's going to face a certain slope, and that slope is going to be given or computed by f of x at AB. So it looks like here in our example, so it's in magenta here. So if you draw the tangent line in that direction, parallel to the x-axis, so it looks like here my slope would be negative. So if you say a goat, let's go down, let's go in the same direction as the x-axis, then the goat is going to go down on the graph. Okay, so, and then meanwhile, if you compute f of y at AB, so if we're going back, if the goat goes back at the point AB, f of AB, now if you draw the tangent line parallel to the y-axis, then that slope is given by f of y at AB. So it looks like here, so if you say goat, move from that point in the direction given by the y-axis, so parallel to the y-axis, you're going to be following the slope given by this orange line. And it looks like here, the slope would be positive. So two different numbers giving you two different slopes, one in the x direction, that's f of x at AB, and one in the y direction, that's f of y at AB. So there's only two directions here. Of course, one natural question would be, a goat, what about if you go in any other direction? Is there other slopes? And the answer is yes, actually. But to compute those, you would need what's called directional derivatives, which are just a linear combination of f of x at AB and f of y at AB, but this is not going to be a topic of discussion for this class. So for us, two numbers, two slopes in the x direction and in the y direction. And again, here, this is like very, very similar to what's going on for a function of one variable. If you start at a point A inside your domain, you compute f of A, you start at the point A f of A. When you compute f prime at A, you're getting the slope of the tangent line. And of course, here there's only one direction, there's only one variable. So that number is the slope of that tangent line. But here now we have, for functions of two variables, two partial derivatives, two different slopes. All right, this goat is having a great time. All right. Now for the next section, there's a couple of points on the graph that are very, very important in practice for us. And those points are going to be maximum and minimum, because we want to maximize or minimize some quantity depending on the application that will interest us, or that I will force you to be interested in. What do they mean? Like, what is it to be a maximum or a minimum for a function of two variables? So first, I have an example here of a function, which is e to the power minus x squared minus y squared. Don't worry about the equation here. I already drew the graph. We will never ask you to draw the graph. This is something that is way too complex anyways. So we can see that at 0, 0. So 0, 0 here, if you start at 0, 0 and you compute the output, you're at that point. So if we bring the goat there, okay, what do we see here? Well, here at 0, 0, you're on top of a little mountain. So if you're on top of a little mountain, this is, of course, an example of a local maximum. So again here, visually, what is a local maximum? It should be very intuitive. If you look at your graph, which is like the surface, which can be thought of a surface of a surface that floats in our tree. If on your surface there's top of little mountains, then of course these little tops corresponds to a local maximum or relative maximum. And one thing that is very crucial, because at some point we want to move from here's the top of a mountain, to let's compute where the top of the mountains are. If we bring our goat to the top of the mountain, you can see here on this graph, if I move in the x direction, if I only look at this function in the x direction, I can think about this graph as being simply the top of that little bell curve. And you can see that the partial derivative in that direction, because when you look at your function and you only let x vary, so you only move in the direction given by the x-axis, you can see that the partial derivative in the x direction is 0. And you can see that you're on top of a parabola bell curve type shaped curve. And then if you do the exact same thing in the other direction, so if you start at the top of that mountain and you wonder what is the value of the partial derivative f of y, then again, in that other direction, if you just move parallel to the y-axis, you're going to be again on top of another parabola or a bell-shaped type curve. And again, the partial derivative now in that direction, which is given by f of y, will also be equal to 0. So all that just to say that when you have a local maximum, like represented here, it looks like the partial derivative, f of x and f of y, are both equal to 0. And in particular, also, you can see that in both directions, we are on top of some parabolas, like in the magenta direction or in the orange direction. Now let's go and look at local minimums. So now I have another function given by x squared plus y squared. Again, we're not thinking about the equation here. I'm giving you the graph. The graph of this function, it looks like a parabola, but it's a 3D analog. It's called actually a paraboloid. Don't need to worry about the name here. So in blue here, I have the graph of my function. And at 0, 0, if I look at 0, 0, I can see that I am at the bottom of a bowl or at the bottom of a lake. So if you have your graph of your function, and anywhere on the graph where you're at the bottom of a lake, at the bottom of a bowl, that corresponds to a local minimum. And again here, if I bring my goat okay, to that point, I can see that if I move in the x direction, I would be following this magenta parabola. And then, of course, the partial derivative f of x is equal to 0. So it's flat there in that direction. And if you move only in the y direction, you would be moving in the following the orange parabola. And again, the partial derivative at that point would be 0. So just like local maximum, the partial derivatives for local minimum in the x or the y direction are both equal to 0. This is absolutely crucial, and this is supposed to seed the idea of how you're going to compute these local min, local max. Well, the basic properties that they both share at this point is that the partial derivatives are both equal to 0. Actually, there's other types of partial derivatives where the partial derivatives does not exist. But for our models, in our applications, all the critical points and all the local min and local max that we're going to study will be given by partial derivatives where both of them are equal to 0. But there's other type of more fancier minimum and maximum. So again, visually, local max, top of a mountain, local min, bottom of the lake. Okay, so this is like the most important part. And bonus information here, or too much information, depending on your on your on your on your point of view. It's just like, if you go on a date and you reach the top of a mountain and you say to your partner, "Oh, did you know that the partial derivatives here are both equal to zero?" There's a good chance that you're not going to get a second date. But anyways, I always think about it when I get to the top of a mountain. Well, I rarely get to the top of a mountain. I'm way too out of shape. But anyways, if I was getting to the top of a mountain, this is what I would be thinking about. Anyways, okay, so top of a mountain, local max, bottom of a lake, local min. So we can summarize some of the ideas that I've just talked about in the following fact that will lead to the notion or the definition of a critical point for a function. If you are dealing with a local min or local max, so in general, when we're bundling the two, we're calling those relative extremums. So for local min and local max, if the function f of x and f of y are nice in the sense that they exist and they're typically continuous, then their value are going to be equal to zero. So if you have a local min, local max for an equation where the partial derivatives are nice, you're going to get those relative extremums. At those relative extremums, the partial derivatives are going to be equal to zero, just like we saw with our goat, at the top of the mountains or the bottom of the lakes. So, and actually any point that satisfies this condition where f of x is equal to zero and f of y is equal to zero is going to be called a critical point. But be careful, a critical point will either be a minimum, a local minimum, local maximum, or there's a third scenario here. You could be talking about a saddle point. So what is a saddle point? Of course, saddle point comes from, like a saddle, like when you're riding a horse. So it's really shaped like a saddle. So for example, if you look at this equation, y squared minus x squared, again, don't worry about the equation here. Just we have the graph. If we look at the point 0, 0, so if you are at the origin, so let's bring our goat at the origin here. So here at 0, 0, if we move in the x direction, we see that we're on top of this magenta parabola. So the partial derivative is equal to 0. But if you move in the y direction, you're at the bottom of this orange parabola where the partial derivative is also equal to 0. But here we see we have a combination. So in one direction, you're on top of a parabola, but in the other direction, you're at the bottom. So this is an example of a saddle point. You can write the function there. You can really put your leg, along this magenta parabola, and then you're going to be riding this graph comfortably and safely where, your belly and your back is going to be following or laying down on the orange parabola. So there's really three types of critical points: local maximum, local minimum, and saddle point. And for now, the only thing that is crucial is that you're able to, for this video, is that you're able to distinguish visually what they are on the graph. If I give you a graph, top of mountains, local maximum, bottom of lakes, local minimum, where you can ride the graph, where there's a saddle on the graph, saddle points. But then now the real question, the natural question that arises are if you have a function and you have the equation for a function to variable, how do you find and compute local minimum, local maximum, and saddle points? And this is what we're going to do in the next video, where we're going to move from visual stuff to computation. This is going to be very exciting, of course. All right, but for this, very nice, write the graph of a function to variable with our little goat. That's it, that's all. Bye-bye.